carefully. So it's time. I'm just gonna wait 1 or 2 more minutes because more people are showing up, and then we can start maybe in a minute or so. Okay, so I think we can start now. Hi, everybody. I'm Sabo Ali Madadi. I'll be the chair for this session, which is the Validation and Verification 5 at ICSE 2020. I want to welcome everybody, our speakers and the audience. We have 6 papers in this track and this session. They range from technical track to software engineering practice to journal first papers. And in terms of the topics, they also cover a broad range of topics. So it's going to be an interesting session. We have 6 presentations. They are going to be 5 minutes each. So we're going to go with the presentations first, and then we're going to have the second half hour dedicated to questions. So if you have any questions throughout the way, please feel free to type that in the chat and specify which talk it relates to, and I'll read them for you at the end of the talks. Or you can raise your hand at the end and I'll call your name and you can just ask questions or participate in the discussion. It's going to be an informal session as well. So please feel free to participate in the discussions. So without further ado, I want to introduce our first speaker. Our first scheduled talk in the program is actually not here, the presenter. So we're going to go to the second presentation, which is titled, How Does Code Reviewing Feedback Evolve? A longitudinal study at Dell EMC. It is a paper from our software engineering practice track, and Max Lamotte from Polytechnique Montreal will be our presenter. So without further ado, I want to invite Max to share his screen and start his talk.
All right, thank you very much. So, hi everyone, I'm Max, as was mentioned before. Unfortunately, the first author of this paper, Ray, couldn't be here today to present, so I'm going to be presenting the paper. I was the second author, but Ray would have done this justice. I'll do my best. So to start with, we first set out to understand what code review is. So the author in the picture that you see here first uploads a patch to a code review platform where reviewers will get a chance to analyze the code and provide feedback. The author is then able to address the reviewer's comments, and the cycle continues until both the reviewer and the author are satisfied, and finally they can merge the patch into the code repository. Naturally, we kind of assume that developers grow up over time and get better at what they do. So the assumption is that the developers kind of shift their focus from comments with less importance, like language details, to those that are more context specific, like software architecture, for example, once they gain some experience. But we don't really know this for sure in practice. So that's why we need to understand the topic of code reviews over time. So if we only do this for one patch, we could just read the comments manually and gather what people are thinking. But when we try to apply this at scale, let's say with thousands of reviews or hundreds of thousands of reviews, we really need automation. So for example, by using NLP. So our paper aims to automate the topics in order to make better use of code reviewing repositories. So we use LDA, and our model training technique automatically discovers a high level understanding of code reviews. So to that end, we study the evolution of code review feedback through a proprietary software project at Dell EMC. That included over 94,000 comments over the span of 4 years. So that was the SEIP part. But to complement this, we also look at an open source project, OpenStack Nova, which includes 151,000 comments over 6 years. So in total, we look at over 248,000 comments collected over 10 years of data. So to find out how the code reviewing content actually evolves, we first set out to explore how the community as a whole shifts their focus as time passes by. So here's one example. There are many more in the paper, but I'm concentrating on one here. So code review process topics generally refer to like politeness comments that would be something like "I'm done" or "Thank you" or "That looks good to me." And this trend, it shows that the community spends less and less time on these boilerplate responses over time. So we could say that members are exchanging fewer niceties on the platform, but really they're concentrating on what's important to them. So maybe they have more offline discussions, either in person or in chat systems, so they don't really feel the need to say thank you or done anymore. So following up on this, we could use sentiment analysis on the comments to get a better understanding of the nature of the change, but we don't actually do this. So in summary, for the evolution of the community, we find that the topics covered by reviewing feedback are continuously evolving at Dell EMC. So the topic models that we have kind of highlight these evolving trends, and they often coincide with project events of significance, like people leaving or new people coming in. So next up, we discuss how individual reviewers evolve as they become more experienced in the project. So looking at the same topic of code review process, so the thank you and stuff that we discussed before, we find that more experienced developers use fewer comments that are related to the code review process. So that the new developers kind of look at that, but more experienced developers kind of avoid it. So it's not to say that people get less nice when they become more experienced, but instead, previous studies have actually shown that the code review process comments are not as helpful as more context-specific comments, and people kind of seem to get that as they become more experienced. So the trend at Dell EMC seems to suggest that developers also follow this trend at Dell EMC. So in conclusion, for individual developers, the reviewing behavior also evolves as the reviewers accrue experience. And our topic models show that experienced reviewers specialize in different ways according to the needs of their community. If you have any questions, please feel free to ask. And if you want more details, of course, feel free to read our paper. Thank you very much.
I'll try to simulate the real conference for you. So thank you, Max, for the great talk. It's very interesting. So again, I want to remind everybody to type their questions in the chat or keep them for the second half of the session that's going to be allocated to Q&A. So we're going to move on to the next paper, which is entitled Nessie Automatically Testing JavaScript APIs with Asynchronous Callbacks. This is a paper from the technical track, and our presenter is Ellen Arteca from Northeastern University. Ellen, please start.
Sure, I'll just share my screen. All right. So I have my little timer. So hey guys, so I'm presenting our work on Nessie, automatically testing JavaScript APIs with asynchronous callbacks. This is joint work with Sebastian Harner and Michael Prattle at the University of Stuttgart and Frank Tipp, my advisor at Northeastern. So what are we doing with this? So we're looking at the problem of how do we generate tests for JavaScript APIs with asynchronous callbacks. So I'll quickly go through some intro and background together with an example. So JavaScript has APIs with async callbacks. So first here we see the import of a module that provides functionality for working with the file system. Now we see a call to read JSON, which is a method in this library. So this is an asynchronous file read. It dispatches the file read, throws it on the event loop, and then continues with program execution. So now the file read is happening in the background, and we print the next print statement that's in this program. And then after the file read is done, then the callback, which is this argument to the function, which is also a function, will execute, and it prints done reading the file. So you see that the print statements are not in the order that they occur in the actual program. So how do we generate tests for these APIs? Well, enter our tool. So Nessie generates the async callbacks. So that's the function arguments, which themselves are functions. Specifically, Nessie generates nested API calls. So what that means is that we have API calls inside of the body of the callback argument to another API call. So here we see output JSON inside of the callback to read JSON. So why do we do nested API calls? Well, this is more representative of the intended API use, and it's more likely to generate sensible arguments. So here's an example of the intended use of the read directory function in fsextra. So this is just saying read the current directory. The callback to this function takes two arguments, the second of which is a list of all the files in the directory it just read. So in this case, what's happening is that inside the body of the callback, we're doing something with each of the files in the directory. So in this case, reading the file. But this data flow between the outer function and the inner nested function is common, and that's how the API is intended to be used. So the current JavaScript API testing doesn't provide this functionality. So we're the first that provides both synchronous and asynchronous callback arguments and both nesting and sequencing. So I'll just explain the pipeline of our test generator by way of an example. So the first phase is an API discovery phase. So what we're doing here is we're getting a list of all of the functions in the library that we're testing, and we're representing these by way of abstract signatures. So the abstract signatures contain the number of arguments, and then for each argument, if it's a callback or not, and if it is a callback, whether or not it's asynchronous or synchronous. The second phase is the actual test generation itself. So that takes abstract signatures as an argument. And the first step in the test generation algorithm is to select a function to test. So in this example, let's just choose ensure file randomly. Then we select a function or a signature for this function and generate arguments for that selected function. So in this case, we see the first argument is not a callback, and the second argument is a callback, which matches the signature. Then we execute the test and observe in this case that the callback is executed. So what that means for us is that there's two valid extension points to this test. First, we can extend with a nested extension inside the body of the callback itself. And second, we could also extend after the call. So this would be a sequenced extension. So the algorithm chooses an extension point randomly. In this case, we'll choose the nested extension, and then we loop through the algorithm again. So let's choose another function to test. This time we'll choose read JSON. We'll choose the first signature. Then we generate arguments for the selected function. And then we just insert the code that we just generated in the extension point that we previously specified. So you'll just see the code we generated for read JSON is now in the body of the callback in the previous test. So that's how we build our tests. We also do some mining of API usages to have a better representation of the way that developers actually use APIs. But we don't have time to talk about that here. So how well does this work? We tested Nessie with 10 file system and promise libraries that have asynchronous APIs. So that's just two applications in JavaScript that have a lot of asynchronous APIs. We evaluated the effectiveness of the discovery phase and found that with automated discovery, we find 60% of the documented signatures that expect callback arguments and 38% of those that do not. We also did a test to see the coverage that we achieved and found that Nessie achieved slightly higher coverage than the previous state of the art, but with many fewer tests required to reach this coverage. And we also evaluated how well we could find behavioral differences with regression testing and found the same trend. So Nessie needs fewer tests to reach the same coverage or the same behavioral difference counts. So in conclusion, we have built Nessie, the test generator for asynchronous JavaScript APIs, which support both sequenced and nested API calls. And we achieve slightly better coverage and behavioral difference tracking than the previous state of the art with many fewer tests. Thank you.
Thank you for the great talk, Ellen. We're gonna make a switch in our topics, go to AI. Our next talk is titled XAIS, Executable AI Semantics. It's a paper from our technical track, and our presenter is Richard Shumi from Singapore Management University.
Yes, hello everyone. Thank you for the introduction. I'm Richard Shumi from Singapore Management University, and I'm going to present our paper XAIS, Executable AI Semantics, which was joint work with Sun Jun. First of all, what is our executable AI semantics? It's a formal Prolog specification of an AI framework. It is written in logic. It captures the behavior of almost all layers of TensorFlow. It is executable in the sense that it can make predictions in a similar fashion as it can be done with an AI library or framework. And we showcase applications like test AI model generation or the validation of AI models to check if the architecture or arguments are consistent. We do this with preconditions within the specification. To motivate our specification or semantics, AI systems have become increasingly popular in recent years, but the reliability of the underlying frameworks can still be questionable. Many users just assume that the underlying AI framework is correct, but a bug could potentially affect all associated AI systems. And the AI frameworks can be really complex in terms of millions of lines of code, and the inner workings of layers are still often not really completely clear or just poorly documented. So it makes sense to have a high-level specification that can be really compact, since it doesn't need any optimizations, and this can help really to get a better understanding of the inner workings of layers. To give you an overview of our semantics, we have specified 72 TensorFlow layers, including of 7 non-deterministic layers of various different types, like convolutional, recurrent, pooling, activation, cropping, dropout layers. And in total, the specification consists of 3,200 lines of Prolog code, which is quite compact due to the high reusability we could achieve. And here we have an example specification of the dense layer. It can be seen it consists of a number of rather simple predicates, and these predicates basically define the relation between the arguments with subpredicates and built-in predicates from Prolog. Based on such a specification, we can then perform predictions by just making queries, and Prolog will run a unification algorithm to give us a prediction result. One of the major applications of our semantics was the test AI model generation. So we apply a fuzzing approach that randomly connects layers and also randomly produces layer arguments in order to get quite diverse test models. And this algorithm works by readily finding valid models by incorporating feedback from the semantics. Then these generated AI models might be used for a number of verification tasks, but we mainly use them for a specification-based differential testing approach for the layer implementations. So on the one hand side, we just execute the AI library with a TensorFlow program, and on the other hand side, we do the same thing with our semantics, and then we can just compare the output for a given model. Another application is the test AI model validation, where we check if a model is valid in terms of the structure and the arguments. Many layers have like requirements like a specific shape. Here we can see we do these checks with preconditions, like the one shown here is for dimensions. And then when a model is executed, all these preconditions are also checked, and the error message is produced when there is an issue, and this error also highlights the location within the model. Finally, we have also implemented a graphical user interface that showcases our applications and performs the model generation and the validation for given models. To sum up my talk, we have developed an executable AI framework semantics called XEyes that captures the behavior of 72 TensorFlow layers. We have illustrated 2 applications: the test AI model generation for AI framework testing and the model validation to find issues in invalid AI models. We have revealed 14 issues and bugs in TensorFlow, including bugs in really common application activation functions, and our semantics is available online in the following GitHub repository. Thank you for your attention.
Thank you, Richard, for the great talk. Next, we have a paper titled Towards Boosting Patch Execution on the Fly. It's a paper, again, from the technical track, and our presenter is Mingxi Zhang from Meta.
Cool. Yeah. Hello, everyone. This is Mengshi from Meta, and in this talk, I will present our research work towards boosting patch execution on the fly. And this project aims at improving automated program repair systems. And first, I would provide some basic context of automated program repairs. So basically, the APR systems follows a patch generation and validation paradigm. And here we prepared a diagram to demonstrate the general workflow. So the APR takes a buggy program as input. Then it analyzes the program and generates patch candidates. In the next step, a patch validator checks the candidates and sends the plausible ones to developers to manually check their correctness. And here, plausible means the patches which can pass validation. And in academia, people proposed multiple validation methods like testing and formal specification checking and static analysis. And our work mainly focuses on testing approach since test cases are widely available for software systems. And moreover, a good APR system means it can find the plausible patches and can find them as quickly as possible. So intuitively, generating more patches is more likely to find the plausible ones. However, it will increase the validation cost, which hurts the system's effectiveness and efficiency. So in this diagram, the patch generator generates tons of patch candidates, which gives the validator a big headache. So reducing APR cost is a meaningful and critical way pacing to achieve practical APR. And we found we are not alone. And there are some existing efforts to reduce the cost, and we summarize them as two directions. So one is to reduce the number of validated patches by photo localization and machine learning or data mining and constraint solving techniques. And the second direction is to reduce the validation time spent on each patch by sharing the same JVM session across multiple patch executions, like prioritizing test executions for each patch using historical information and reducing the number of test execution for each patch. To conclude the existing works, we can have an impression that people want to get a more powerful patch generator and a more efficient validator. So we want to reduce the APR cost from another angle, that we would try to leverage on-the-fly patch execution information to help better prioritize the remaining patch executions. And this is orthogonal to the aforementioned approaches. And we know that the validator can fail a lot of incorrect patches. And our high-level insight is that these incorrect patches are not created equal, and we should utilize such differences from these wastes to make the system more efficient. And specifically, if an incorrect patch can make any failing test pass, it implies this change should be related to the bug, and it is more valuable than the others. And we treat this kind of patches as high-quality patches and the others as low-quality ones. And then our idea is to promote the ranking of the remaining patches similar to the executed high-quality patches and degrade the ranking of the remaining patches similar to the executed low-quality patches. And these slides will show a big picture of our technique as the APR. And suppose we already collected a set of validated patches. We first evaluate their quality according to their validation results. Then we use this patch set to compare with each unvalidated patch candidate and compute their similarity tuple. And in the next step, we use a formula to project that tuple to a priority score and use that score to sort such candidates. And lastly, we evaluate the top one candidate and add it to the validated patch set. And if a patch is plausible, SE APR will share it with developers for manual review. And please note that our technique supports cold start, and in such case, the first patch can be selected according to the default order. So in our work, we use defects4j to evaluate SEPR, and defects4j includes around 400 real bugs and 20,000 test cases. And this is the most widely used subject systems for recent photo localization and program repair studies. And we used a number of validated patches before finding the first plausible or correct patches to evaluate ICAPR's effectiveness. And we considered 31 APR systems targeting Java program, and 17 systems are applicable to Defect4J and publicly available. And moreover, we exclude ACS, Dynamoth, Nopal due to the limited patch generation, and Semifix because it stops patch execution after finding the first plausible patch. And finally, we evaluate ICAPR on 13 APR tools. And here we show the main result of ICAPR. And from these two tables, and we can observe that ICAPR can substantially reduce the patch execution for finding the first plausible and correct patches on almost all APR tools. And this result proves the effectiveness of ICAPR. And due to the time limit, and we just present our insight, high-level design, and main experimental result of ICAPR, and we highly encourage the interested audience to get more technical details and more experimental results from our paper and long presentation video. And thank you so much for your time.
Thank you, Mengxi, for the great talk. Last but not least, we have a paper titled Diversity-Driven Automated Formal Verification. This is another paper from our technical track, and it actually won an ACM6 Soft Distinguished Paper Award. Our presenter is Emily First from University of Massachusetts Amherst. So please start the talk whenever you're comfortable.
All right, thank you. Okay. Hi, my name is Emily First, and I'm a PhD student at the University of Massachusetts Amherst. Today, I'm going to talk about my paper, Diversity-Driven Automated Formal Verification, which is joint work with my advisor, Yuri Brun. This work presents a tool called DIVA that leverages the diversity in different models of proofs to verify more properties software systems automatically than ever before. And with that, I'd like to tell you why you should care about automating the formal verification of software. Formally verifying software is important, especially in the high-stakes domains where buggy software can cost people their lives. And so it is critical to prevent that. A promising method for building correct software has been to use programming languages that are designed to support verification, called interactive theorem provers. Coq is the language that we focus on in this work, since it is used in many software verification efforts. With Coq, a programmer can specify a theorem about a property of their software and write a proof script, which is a series of proof tactics that Coq uses to attempt to construct a proof of the theorem. You've managed to complete the proof if you're able to get to QED. These interactive theorem provers have already had a significant impact on industry, from using formally verified compilers and cryptographic libraries to building formally verified solutions offered as a service for clients, providing tools for users to detect vulnerabilities. These are some companies that have been using interactive theorem provers to ensure safety and improve performance of systems. Still, even with the help of interactive theorem prover, the effort required is often prohibitive. Verifying code requires a lot of time and a lot of proofs in proportion to your code. For example, for the Coq verified C compiler CompCert, the proof is more than 8 times bigger than the compiler code itself and took 3 person-years of work. So as a general rule, because of the great expense of verification, virtually all software the companies ship today is unverified. If we can cut down the time programmers would need to spend on writing proofs, that would be a big win, because we'd be making progress towards enabling more verification. Our tool Diva, together with prior work, has reached a new milestone, approving over 1/3 of all theorems completely automatically on the CoqGen benchmark, which is the largest available collection of real-world Coq projects with a test set of over 10,000 theorems. Following prior work, we use machine learning to model existing proof scripts to perform next tactic prediction. A partial proof script serves as input to a model that has been trained on a corpora of proof scripts, and it can predict the next likely step of the proof. We combine this with search to synthesize complete proof scripts. The question remains, which proof script model do we use? Do we use the one that has the best overall success rate, But what if the particular theorem we want to prove is proven by another model? Our tool DIVA explores using multiple diverse models and how to leverage the diversity in those models to enable more verification. Usually with multiple models, you think of ensemble learning, and in a typical ensemble learning setup, you have a set of models that differ in some way, and you consolidate their predictions and they vote on a single prediction to use. But one of the problems with that is typically the majority of models have to make the correct decision. If only one correctly performs a particular task, the other models will drown it out, and the ensemble will fail on that input. We overcome this problem in the formal verification domain. For the downstream task of generating a complete proof script, we can let each diverse model use search to attempt to synthesize a proof script for a given theorem from scratch. The Coq proof assistant can then unequivocally tell us if a proof is correct, and so we can throw an army of models at the problem, and if just a single one generates the proof, our ensemble can pick that proof out every time. So multiple diverse models in the existence of the proof assistant, a correctness oracle, mean that we don't have to sacrifice proving power, and we don't have to choose between models. So what do we vary to create this diverse set of models that potentially prove complementary sets of theorems? Well, we can vary what aspects of the training data we encode, such as the proof script and the current proof state, and the learning parameters of the model itself, such as the learning rate and the embedding size. We implement and evaluate these types of variations in DIVA. Through these variations, we generate 62 models that together make up DIVA. Using the diversity of these models was a big success and allows us to prove 77% more theorems than the single best performing model. And together with the prior tool Coq-Hammer, which instead takes a solver-based approach, DIVA proves more than a third of all the theorems in CoqGIM, which is the largest fraction to date. To run a bunch of diverse models in series would take a very long time, but we develop a method that instead cuts down the mean time to prove a theorem by up to 97%. Our work strongly suggests that using diversity for improving automated formal verification is fruitful and will enable automating more verification. Thank you.
Thank you, Emily, for the great presentation. So we did have one more talk in this session. First, the presenter unfortunately was not able to attend, but the paper was and discovery of environment behavior, and it was actually a journal first paper. So I encourage people to check the preprint and the video that are available on the website if they're interested. So in the second half of the talk, we're gonna have a panel with all our authors for Q&A. So I encourage all the audience members to raise their hands and ask questions when we call their names, or type the questions in the chat and I'll read those questions. So we already have a few questions in the chat, so I'll start by reading them, but please feel free to, offer your feedback or participate in a discussion at any point throughout the remaining half an hour. So the first question is actually for Ellen from Max. So Max, do you want to ask it yourself or do you want me to read it?
Good.
Sure.
So I'm particularly interested in the API mining part, the part that you didn't have time to talk about in this talk. So I was wondering if you have multiple usages that match, let's say, one specific API that you're looking for in your data set, how do you choose which example you'll use? I'm assuming that, let's say they have the same frequency. Let's say both are equally frequent. How would you make a decision on which one to use for your test, let's say?
Yeah, so that's a good question. So first, I'll just briefly say the way that the mined API usages are represented is it's like those abstract signatures that I described in the discovery phase. So you have the outer function, that abstract signature, and then the inner nested function, same abstract signature. And if there's any data flow between the outer function and then the arguments to the inner function, then that data flow is represented with the arguments. So that's the kind of information that we have in the mined usages. And then to answer your question, it's random. So we just randomly choose one of the represented signatures. Also, fun fact, we tested in the paper what is the effect of using different basically how often we use the mine data. We tested that. So we used it none of the time, and then 25% of the time, 50% of the time, and so on. And we actually found that the results were best when we used the mined API usages only 50% of the time. And the reason for that is because, of course, it's not like every single possible usage of the API exists in the data that we mined. And so if we use the mine data 100% of the time, then we're excluding a lot of possibilities. So
Thank you.
thanks for the question.
So the second question is also from Max, but for Richard. So should I read it, or do you want to go again?
I can ask it. So this is a more general question than I asked Ellen. Like very nice talk, very nice models. So do you foresee more usage for your verification models for developers that use the framework so that they can test their code and verify if they've made errors or mistakes or something, or for the framework developers themselves to, let's say, mine a bunch of repositories, see where people are making mistakes, where people are using the frameworks oddly, and then potentially improving the framework itself? Like, do you see both?
Yes, I see both actually. On the one hand side, for the developers, we are planning on exploring possibilities like automatic model synthesis or automatic machine learning to apply our models basically for given input data and see if we can find good models that would make accurate predictions. And on the other hand side, for the developers, we also look into applications like automated model repair to check if we can fix issues in existing models automatically with our approach. And for the AI framework developers, yeah, we are currently looking into what are common modeling issues in the AI models, and then we can focus on generating such issues more commonly. Right now, we were just focusing on diverse models in general, but it also makes sense to focus more on really common mistakes that are made by developers to also improve the error handling of the frameworks itself.
Thank you for the question and the answer. So the third question we have is from Shane. Shane, I see you're still here. So do you want to ask it, or I can read it for you as well? Okay, I'll just read it. So the question is for Mengxi.
Got this thing working. Sorry. There's a lot of permissions involved, but eventually I appear. Okay. So yeah, Mengxi, nice talk. I was interested in this third row you had in your results, where the numbers seem to degrade rather than improve. And I'm wondering if you had a chance to look at that project and figure out if there's something specific about it that's making your approach struggle. Do you know what I was referring to? Yeah. Okay.
Yeah. And first of all, thank you so much for your interest and great question, Jane. And honestly speaking, yeah, we do see some performance regression of our 2SE APR on the APR tool called Cardumen. And generally speaking, our tool can perform very good on some APR tools, which can generate on average a lot of patches, and also can fix a lot of defects for JA versions. And actually, our improvement is solid and stable. However, for Cardumen, compared to other tools, it generates less patches and can fix less defects for JA versions. So, which means the performance will be will have big variance. So that's why we indeed observe some regression. Yeah.
Does that answer your question? Okay, thank you. So I have a question for Max this time. So you talked about code reviews and how you saw this evolution of how people do code reviews. So as an educator, I wonder what lessons there are that you have for us when we teach and practice code reviews in universities. Is there anything we can learn from that?
So I think the biggest takeaway from the paper is that the code reviews evolve not only like on a personal level, so as you accrue experience, how you review will change, but also as you take part in a community, that community will also change how it reviews code. And so I think one thing we could communicate to students is to be willing to learn from senior reviewers, and to try to learn from senior reviewers, and to try to adopt the community standards for where they're going to be reviewing. So there are like, we can tell students, it's easy to review, to submit a code review that looks at, let's say, code style. But sometimes that's what the community wants. Like what we found actually was that in one of our projects, at some point there was a huge influx of new developers that came in, and they were not following the original code styles of the project. And so the senior developers, which normally would not have been commenting on code style, suddenly started commenting on code style to tell these new developers, hey, like we have a code style, please respect it, here's how you do it. And so just because they were senior developers doesn't mean they shouldn't comment on it, right? Like if they see a problem, they notice it's there, they start commenting on it, and all of a sudden it just improves because that's what the community wants to improve. And so I think one of the things we can teach is just be aware of what your community wants and listen to the feedback, right? Like if someone gives you feedback, listen to it, learn from it, and you as well keep giving that feedback forward, right? Like it's a continuous system where people will teach you something, then you will teach the next generation, and so on and so forth.
Very interesting. So these you figured out from comments, for example, by mining data from repositories mostly, yes?
Right. So it's mining the topics that people would talk about in their reviews. So we used LDA to model the topics that people would bring up in their reviews. And so by looking at how the topics evolve over time, we can kind of tell like what people are mentioning, like on a high level, rather than looking at like low level comments. And so we can see trends evolving in the topics that get mentioned most often, or stop getting mentioned at some points in certain topics.
Interesting. I asked that because another angle we can have on this is, I know it's more difficult, but conducting experiments, empirical experiments, at these companies. I think it was Dell that you took the data, and the data was private, right? So I assume you're one step closer to getting actual developers. So have you given that any thought, or is that in progress?
So what we did for the experiment was that we, like at the time, we were looking at how managers were looking at the comments. So like the managers were trying to get an idea of how are people using code review, and how can we use that to influence or see how the project is going, basically. And so that was the way it was looked at internally. You're right in that it's a proprietary system, so we couldn't share any of that information, which is why we replicated the study on Nova, and like we saw different trends, right? Like the point wasn't that the trends are all the same on all projects, but that every project seems to be displaying its own trends, and that the information we can extract from the topics is more about how we can inform that specific project and the developers of that specific project, rather than we can't just make a blanket statement of like, oh, as you accrue experience, you'll definitely stop talking about X topic. Turns out that's not how that works, right? It really depends where you are, who you're working with, and what's happening to the enterprise where you're working.
Yeah. So my second question is more directed at, whether or not you have thought about having a user study that you go and observe people when they're doing code reviews and they're interacting, and maybe, get more information than what you see in the comments.
Oh, you mean like at the time, like when they're actually writing the reviews, like asking them questions like, why did you write this? And like what?
Yeah, so they think aloud, monitor their conversations for the future. I know this is not in the scope of it.
Yeah, that's a very interesting. Yeah, that would be very interesting.
Yeah, thank you.
Thank you.
So I encourage the audience to ask questions. So if there are no more questions, I'm going to ask another question from Emily this time. So I assume the users of your tool will be, of Diva, would be people who are doing formal verifications, right? So very theory heavy field. But there's still people, right? So I wonder, like, how would you use this tool in your day-to-day activities? How do you integrate it with the rest of the tasks that you do, and where does that fit into that cycle?
Yeah, so this tool kind of comes in towards the end. First, you have to write your code, then you have to write some specifications about it. So you have to think a little critically about what are some properties you want to prove. And then we come in and we can generate the proof for you, hopefully.
Yeah, so again, as somebody who's doing human-centered software engineering, I wonder, about the usefulness, right? Because the numbers are impressive, the work is great. But again, I want to know more of your insights about, what would make this be adopted and be used as a mainstream tool in the area, or what needs to be done in order, to have that it's actually deployed and people are using it as a necessity with their development environments.
Yeah,
or
so obviously verification has a way to go before people start adopting it. But if we can kind of start convincing people that, hey, we can take some of the burden off of the programmer for having to write a proof, which is really difficult, then we can, incrementally start automating other parts of the processes. Like maybe there could be a tool that could automatically extract some specifications. I think at least for that aspect, there would have to be a human in the loop to say, oh, yeah, that's actually something I want to prove about my software.
Yeah, it does make sense that you would have the human in the loop. I don't think you can remove the human altogether.
Yeah, but at least for the actual proof itself, if it's something that is actually true, then you might not actually need the human. And that's where our tool can kind of come in and help save time, and hopefully more researchers continue on that path and help with that automation part.
That's great. It's very cool. Thank you. So again, please ask questions. Otherwise, I'll just keep asking questions. We have about 13 minutes left. Yeah, Max.
Yeah. So I have a question for Emily, actually. So super interesting talk, like wonderful talk. I just want to say, like, your talk was amazing.
Thanks.
And your subject is super interesting. But my question is, I guess it's a two-parter, but I'll try to shove it into one. If you can identify which models are complementary, can you also identify like gaps in the model? So can you say like none of the models are able to prove this type of proof? And then could that be used for future proof builders, like model builders, to say like, okay, I'm going to build a model to prove this. No one can seem to get this one down. Like, can I do it?
Yeah, I think that's a really good point. It's definitely possible to sort of look at the proofs that aren't proven and then maybe make some general classifications about them. For this work, we did not do that. It's part of my future work, personally, to go ahead and do a sort of qualitative evaluation of what sort of proofs we do well on, what sort of proofs we don't do so well on. But I think, yeah, that's a really good point. And yeah, I think if it's a particular type of proof that requires a certain proof method, maybe you can gear your models towards solving those. But the good thing is that you can use multiple models and you can still get the previous proofs that you got before.
Yeah, so that was the second part of my question. Can you see a world where we're iteratively just like building more solvers so that eventually we get like from, I think you're at like 33 point something % right now.
Yeah.
Do you think can you see a world where we're going into like 50, 60, 70% solvability, or is that just like way far down the line?
I mean, that's the dream. But yeah, I do see a world where that's possible. And, you know, part of it's using different types of models with different like architecture. So the models that we're using, they're mostly LSTM, RNN based, but there's a lot of exciting work in other theorem provers where people are using really large transformer models. And so that's something that I'm currently exploring as well for languages like Coq. And yeah, so I think it's possible. I'm optimistic.
Excellent. Glad to hear it.
Yeah.
Thank you.
Thanks.
Thank you. Other questions from the audience? Yes, Ellen, please.
Yeah, so I had a question as well for you, Emily. So this is like the automatic generation of the proofs, right? But do you know, because this is totally not my field, but like I wrote a bunch of Coq, and in my experience, formally representing the system that you want to reason about is also a ton of work. So do you know if there's any work on automatically generating that?
I'm not super familiar with work on automatically extracting those specifications. There's other work on, you know, premise selection. So what's like a previous theorem you've proven that could be useful in your proof. But yeah, I'm not familiar with in Coq specifically if there's work on extracting.
No worries. I was just curious.
Yeah. But it is an interesting area to explore.
Because then you could automate the whole pipeline if you automatically got specifications and the proofs.
That's the dream. Yeah.
Thanks. So not completely related to that, but in the similar realm, I have a question for Richard. So I was wondering how much manual effort is required for getting the specifications for the neural nets?
That's still quite a lot of manual effort, especially since we use the TensorFlow documentation as a basis for building the specification, and unfortunately the documentation is not really that sufficient in many cases. So some things are just poorly documented there, or even wrongly documented, and even simple, commonly used activation functions or so had like a wrong documentation, and this made the whole process quite challenging. So it was like a manual effort of quite some months, even though the specification itself is quite compact in terms of the number of lines of code.
Yeah, I bet it was a lot of work. So were there any assumptions you have to make considering, the incompleteness of the documentations and, the general nature of the domain? Did you have to make some assumptions to make the specifications work and make them sound? Or?
Basically, we specify most of the layers on the assumption that we have given static weights. So to be able to make also exact predictions with the models that can be then compared to the actual predictions with the framework itself.
Makes sense. Thank you. We have another question from Shane. So Shane, do you want to ask it or do you want me to do it?
It's working. Okay, great. Yeah, I just I was thinking about Ming-Chi's approach, and you have this loop back to start the ranking process again. And I probably just missed it, but what's the stopping criteria for that loop? Do you just go a certain number of times or until you reach some specified cutoff?
Yeah, that's a good question. Actually, our stopping criteria is we validate all the patches. And our goal is to share the plausible patches to the developers as soon as possible.
Thanks. So following that, I was wondering if you can tell us a little bit more about your scoring mechanism. So what are the important factors in the score and how did you come up with them?
Sure, this is a good question. And basically, is we already have a collection of validated patches, and we know their results, right? And for example, one patches can help some, existing failing test pass, and we think, okay, this patch is very interesting and that is valuable. And for the rest, and not so interesting. And for the first one, we call it high quality patches, and second one is low quality patches. And now I have a one patch candidate, which is not validated yet. And one thing I would like to do is, compare the unvalidated patch candidate with the existing ones. And actually, the similarity metric is we want to see, what program entity are changed for these patches, like the statement or method or Java classes, yeah, this kind of things. And given two patches, actually we can learn the the overlap of the entities and the the unique entities of them. And this is true value, and we can add another dimension is the validated patches is high quality or not. Actually, we can have totally 4 values, right? And that is we call similarity tuple. And then we will use a formula to project this tuple as a score. And then we will do that for all the remaining patches candidates, and then sort them to select the top 1 candidate and do the evaluation.
Interesting. Thank you.
Yeah.
Any final questions from the audience? Then maybe I'll ask a quick one from Ellen. So for your extension points, I saw that they were inside the closures, inside the callbacks, right? So do you generate something, function invocations that take callbacks as arguments?
Yeah, so there's 2 types of extension points. So one, like you noticed, was in the body of the callback, and then you can also have an extension point after. So that would just be like one function call and then right after a different function call.
Okay.
So yeah, so basically when we're generating tests, if the signature that is chosen randomly has a callback argument, then it will have a function as an argument. And then when we run the test, if we know, so this is the feedback directed part. So if we notice that the callback is actually executed, then we say, okay, the body of the callback is a potential extension point. But if we don't see that it's executed, or if there was an error, then it's not a valid extension point.
Okay, so that was my actual question, that how do you detect if the callback?
Oh, yes. Okay, so that's part of the discovery.
No, I didn't say it. So I was just building to that. So I wanted to confirm.
Okay.
And this is my real question.
Okay. Yeah, so the discovery phase, basically it works by, we iterate over all of the functions that are in the library. So that's just the dynamic properties of the library object. And then we just try a callback that prints for each argument. Like we just iterate over them in a loop. And then we just note like, oh, does the print statement happen when the callback argument is the first one or the second one or whatever?
I see.
So yeah.
Interesting.
And then to tell if it's synchronous or asynchronous, we also just note the order that the execution prints. So remember the example where it shows, oh, the first print statement is the one that's after the callback. Well, then we know that it's asynchronous.
Makes sense.
Thanks.
Yeah, thank you for the clarification. So we're at the end of our time. If there are any final quick questions from the audience or our speakers, this is your chance. Okay, then I would like to thank everybody. I want to thank our speakers, all great talks. I really enjoyed hearing about your work. I want to thank our student volunteer, Manish, who helped with the session. And I want to thank all our audience members for participating and the great questions and discussions. I wish you all a great day, night, wherever you are, and hope that you enjoy the rest of the conference. Thank you, everyone. And yeah, take care. This concludes our session. Thank you for attending.
Thanks for chairing.
Thank you.
See you.
Bye.